So we're now in our gauge theory section, and my goals here, the goals are, well, first thing I'm going to do is extend to Yang-Mills theory. And to do that, we needed to do the group theory that we did last time, the little bitty baby group theory. The other thing that we want to do is, I gave you various rules for QED in the past, but those rules didn't follow from what I taught. In fact, if you applied what I taught, you would get the wrong answer. So it's to teach it, right? Okay. And the third thing, well, we're not going to go in tremendous depth, is I want to do a survey of the major lessons. There are lots of things that everybody should know about gauge theories that I just want to make sure we all go through and get them. Okay? So there's where we want to go. So, Nonableian, or Yang-Mills. Okay, so we'll do all the SUNs all at once. Previously we had done QED, which is a U1 gauge theory. So let's now just do SUN. Yang-Mills implies SUN. Okay, and it just basically takes an invariance and makes it a local invariance. So we want a local symmetry, which would be something like psi goes to U of X psi. And if we're in SUN, psi is some psi 1, psi n, there's n of them. So this is a 4 by 4, or n by n matrix, and we'll parameterize it as U is e to the minus I alpha of X dot lambda over 2. I'm sticking a factor of 2 in there. That's where I haven't been writing that in the past. It's clearly convention because alpha is completely arbitrary, but it makes some formulas look nicer as we go along. Okay? So, if we want this to form an invariant, we're going to want to have Lagrangian is psi bar I d slash psi. That goes to some psi bar prime I d slash prime psi prime. We know the psi primes, so this becomes psi bar u dagger d slash prime u. And there's there's no psi. So this tells us that our goal is to write d slash goes to d slash prime, which is u d slash u dagger. Okay. So we want, remember that's how something in the adjoint representation transformed u dagger. Or another way of putting it is that we want d slash psi to go to u d slash psi under this change. So this is the idea that it's covariant, that d slash psi transforms the same way as psi does. Okay? This will require SUN gauge fields. And the goal is to construct their transformation properties. So since the derivative is the piece that gives us trouble, d mu u goes for small u, like minus I d mu alpha of x dot lambda over 2. So we want something that can cancel that guy off. So the obvious thing to do is to take d mu is d mu plus ig a mu, and we'll put a factor of 2 there also. Okay. So then when you get the d mu acting on u, you can cancel it by a gauge transformation of A. Okay. So to force this, let's make it work. So we want d mu prime equals u d mu plus ig a dot lambda over 2 u dagger by our condition, but that's by definition d mu plus ig a prime dot lambda over 2. Okay. On the left side there, this turns into, the derivative doesn't have to act on the u's, but it could. So there's two pieces, plus u d mu u dagger, and then plus ig a dot lambda, but I have u, let's write that out better, u a dot lambda u dagger over 2. So we see two things. In the U1 case, U was just a phase that went right through the gauge field. Here that's no longer the case. This contains a lambda matrix. The lambda matrices don't commute. So we have two terms. We have a gauge transformation term, and we have a rotation. So our rule here is that A prime mu I is no, all right, let's back up. Let's keep it in matrix notation form for the moment. Lambda dot A mu over 2 with a prime is u lambda dot A u dagger over 2 minus or plus u d mu u dagger. Over, let's see, I'm missing my IGs. I want to okay, anyone have questions about it? Let's just do this infinitesimally so we see it a bit for small transformations. for small transformations, u is 1 minus alpha dot lambda over 2 of an I. So that a lambda dot a prime mu over 2 is then 1 minus I alpha dot lambda over 2 lambda dot a over 2 1 plus I alpha dot lambda over 2. And this, the gauge piece is I over G times the derivative of I alpha dot lambda over 2. So the piece we first keep is lambda dot alpha, lambda dot a over 2, and then I end up with plus I over 4 lambda dot a commuted with lambda dot alpha, and then here it's plus 1 over G d mu alpha dot lambda over 2. Let's see, where's my eyes? I'm a little worried about screwing up my eyes too, but I think there's, but I think actually I'm having the cross terms actually don't, because it turns into the commutator. Okay, one sits on this side, one sits on that side, and since the lambda matrices don't commute, I want these things to be a commutator of the two. Okay. So I think I've got it. I am worried about some signs on this because they don't quite match my notes at this moment, but so there's something wrong somewhere. Okay, so I'm working for small transformations, so for infinitesimally, so I'm dropping alpha squared because there's also an alpha squared term out here. Okay, so for large transformations, the rule that we want is this one, which is valid for all scales. Okay, and if I wanted to, I actually will write the answer, the general answer, true. But this here commutator, if we use lambda I, lambda j is 2i fij k, lambda k. So these symbols fij k are antisymmetric, totally antisymmetric. And they're the structure constants of SUN, whatever they are. So for SU2, those are the epsilon ijk, and then there are generalizations for other SUNs. Okay, and then if that's the case, then this is linear in lambda. This one becomes linear in lambda 2 after the commutator. This one is linear in lambda, so I can pull out. So I take the trace of lambda I to get rid of it, and I can pull out a I mu prime is a mu, and here I'll just jump to my notes so there may be a sign issue somewhere around here, plus 1 over g d mu alpha I plus fi j k a k alpha j is what I have copied down. So this is the gauge transformation part. This is the rotation part. And the full one, a prime I mu, is one of these rij's, a j mu minus 2I over g. No, it's not 2. I over g. Trace lambda I u d mu u dagger. Okay. Okay. This Rij is something that we did before. It's the rotation matrix. It's 1/2 trace u lambda I u dagger lambda j. We did this in SU2, showed that it was an O3 rotation matrix. That's the generalization to SUN. Okay. Okay, so the new piece is this. There's a nonlinear piece. That comes back to play an important role later on when we quantize. Okay. There's the only things we haven't done. I haven't shown that this term here is Hermitian and traceless. Okay. These two pieces here are Hermitian and traceless. So since that guy is, this one had better be. It actually is a little proof. In fact, I have it written out. I think I'll skip it. You can probably. Actually, let me do the proof just to show you. There is one interesting technique in that. So just let's do it quickly. Here's the showing the Hermitian is interesting. I want to show that I u d mu u dagger is Hermitian. Okay. Now if I take the Hermitian conjugate of that, I get minus, so if I take the Hermitian conjugate of that, I get minus I d mu u dagger. Okay. So notationally it doesn't look Hermitian. The piece that's a useful trick to note here is that since u dagger u equals 1, that implies that d mu u dagger u equals 0. So if I take the derivative of that, which implies d mu u dagger u equals minus the other one, which is u dagger d mu u, which so let's see, and I can also do the other one too. The u dagger is 1 implies d mu u dagger is minus u d mu u dagger. Actually, that's the better one to use in this case. So if I take this one here, it's again the same proof. D mu u dagger is this guy is minus that. So with the I, okay, so that's a trick I use a lot. So when you have these matrices, that's why it's worth showing it to you. The other one is not, I don't have a nice fancy proof to the traceless. I don't have a good proof. Here's how I do it. When I do it is I write out u d mu u dagger in terms of 1 minus the Taylor expansion. 1 minus I alpha dot lambda over 2 plus dot dot dot, and d mu 1 plus I alpha dot lambda over 2 plus dot dot dot, and this ends up turning into when you do it, it ends up being lambda dotted into something. Okay, the first term is I d mu alpha, but the second term is also that. So you just work out term by term in the Taylor expansion, and you see it's lambda dot something, so it's traceless. Okay, but I've spent more time than I care to admit trying to come up with an elegant proof. So if you want to show me up, you can do that. Something of the order of the above, that you can see it without doing any calculation. All right, so we at this stage we have our gauge field, we have its transformation properties, and we want to write out Lagrangians. We've written out the fermion Lagrangian. How about the gauge field Lagrangian? So the easiest way to do this is to get an F mu nu out that's invariant. Okay? So we're going to have an index I on it, where I is the SUN index, and so we need to come up with one. Okay? So here's the easy way to do it. If I take this covariant derivative that we had before and form the commutator of two covariant derivatives. Okay? Now, that starts off looking like an F mu nu, because it's a derivative mu acting on A nu, and then the other piece gives the derivative of nu acting on a mu. So it starts off looking like f mu nu. We also know that this thing transforms in a covariant way, so it looks like goes to u d mu u dagger, u d mu d nu, u dagger, which is then the original beastie, d mu d nu, sandwiches between u and u dagger. So what we know is that this transforms like the joint representation, just by, since D does, then the product of two Ds does. So it has a good feature. So we're going to define this thing to be Ig lambda dot f mu nu over 2. And so let's just work out what it is. So d mu commuted with d nu. Well, the derivative pieces themselves commute, so the first thing that we get is Ig d mu lambda dot A over 2 nu minus d nu lambda dot A mu over 2. Okay, so that's the first piece, just from the derivatives acting on A. But then there's the second piece, which is plus Ig over 2 quantity squared lambda dot A mu commuted with lambda dot A nu. Okay, so again, those things don't commute because they have different indices on them. So we write this as 2I Fij lambda k ai a mu a j nu. And this lets us pull out Fi mu nu. Well, from the first piece, I just get, so the Ig over 2 is matched, so let's they get dropped. Becomes d mu a nu minus d nu a mu. You just take the piece that's proportional to lambda I here, and you get those guys. Here we have to fiddle the indices around. We want the piece proportional to the lambda matrix. So rewriting this, let me just do it. There's one Ig over 2 disappears. The other over 2 cancels that 2. There's still a G, and I have to rewrite the indices, and I won't do the minus signs in my head. I'll just tell you it's plus G Fij A J mu A K nu. Okay, or if we had a good way, in our book we have this nice way of doing boldface as matrix notation, but it basically, you can write this as lambda dot F mu nu is d mu lambda dot A minus d nu lambda dot A nu plus G over 2 A lambda dot A lambda dot A. All right. Unfortunately, if we didn't have to write those lambda dot A's all the time, it'd be nice, simple notation. And we do that in the book, but I can't write bold-faced here. So. But the key feature here is then that the transformation property is lambda dot F goes to U lambda dot F U dagger. Okay, that's the key feature. And that's true, it's not just for small transformations, that's for big transformations. And we've gotten it from just doing this original one. Okay. So this implies then to form an invariant, if we take 1/2 trace lambda dot F lambda dot F, that goes, that's clearly invariant because that goes into 1/2 trace U lambda dot F U dagger U lambda dot F U dagger. Let's not bother putting the indices on it, which is invariant, and the 1/2 the trace is Fi mu nu Fi mu nu. Okay, so we've got an invariant out, and this way we can write an overall Lagrangian. So this is the Yang-Mills Lagrangian. We have L is -1/4 F mu nu I Fi mu nu plus psi bar d slash minus m psi. Okay, let's see if I can, I can keep them both on the page at once, with F being this and D being the usual covariant derivative, which you probably hold in your head. Okay. So at this stage, I'm not going to explore too much, but you can see not only is there in this diagram, there's an interaction that looks like that with the A's coming out. In this part of the Lagrangian, there are pieces that involve 3 of these, because F has a piece with 1 and a piece with 2, and then there's also a piece with 4 of them. We'll pull out the Feynman rules later when we start doing some calculations. All right, maybe I'll leave it on that one for that part. So there's very quickly, a development of Yang-Mills. Anybody? No. All right, path integral quantization. so this is the fun part. So first point to make is that the propagator does not exist. I'm going to use QED for all these examples for a while, just so I don't have no notational issues, and then we'll come back and we'll do the others. It comes pretty easy after a while. So we have box A mu minus D mu D nu A nu equals J mu. We would like to have box G mu nu minus D mu D nu some Feynman propagator mu lambda is G mu lambda delta for x minus x prime. Okay, let's not do all the intermediate steps, but if you do the Fourier transform, this is basically minus k squared G mu nu plus k mu k nu on some G mu lambda of k has to equal G mu, I guess, J nu lambda. So clearly if you Fourier transform one, you get the other, right? The most general form of G mu nu of k is it could be some a of k squared G mu, G mu lambda, and it can some b of k squared k mu k lambda. Right? No other options there. And so if I just plug through the equations, the b piece dotted into this gives 0, since let's take the k mu into k mu is k squared, becomes k nu over here. These two terms cancel, so the b piece completely disappears, doesn't give anything, and this turns into a. When I do a on it, I get a k squared minus k squared G nu lambda plus k nu k lambda equals G nu lambda, which is impossible. So there is no inverse. Okay. So why is this? Okay, anyone? Did I go too fast on that? I don't know if I'm going too fast or if people have basically seen this or understand it already. Yeah.
Well, when you do the Fourier transform,
yeah.
So you have a delta function, and then you'll have an exponential as well.
Right.
Where does that go?
All right. Basically, I've dropped that on both sides here. Okay. Basically, remember how one does this. You Fourier transform both sides of this. So this has, when you Fourier transform, has an exponential, and this g of k squared.
Oh, so the g is defined as the exponential times.
Well, so no, the exponential's been factored out. Okay. Okay. Let's go back and do it then. Let me write it out. I want box G mu nu minus D mu D nu on integral d4k over 2 pi to the fourth, some g mu lambda of k squared e to the minus I k dot x minus x prime on that side, and on the other side I want g nu lambda integral d4k for 2 pi to the fourth 1 times e to the minus I k dot x minus x prime. Okay, so this is this equation here with a Fourier transform for this. Okay, so now I bring this in, it turns into this equation here, because I take the derivatives, and if this equals that, then I get the right hand side with 1 there. Okay, so that if this condition is true on this function here, then I'll get the delta function sitting on this side. Okay, so that's what I've done. Okay. So basically, I mean, whenever you do a Green's function, you're doing this. The delta function is a Fourier transform of 1. The Green's function then is a Fourier transform of the whatever is the inverse of that, the momentum space equation of motion. So you put some function here that's a general function. You then want this times that equals 1, and this is just with all these extra indices, the equation of motion times Green's function equals 1. Okay. Okay, so the main thing is the why is this important? So this is a fact. Why is it important? Okay, remember we used the propagators when we formed the z of j, which was the integral d phi e to the I integral. Well, let's just shorthand notation, phi o phi plus j phi. We wrote that as that's 1 over the square root of the determinant of o e to the minus j o minus 1 j. Right? That's our basic thing. So o minus 1 is the propagator, and we've now seen this formula enough times, I'm not going to write it. If we try this with E and M, with QED, we get infinity. Or blows up or something. So we can't develop perturbation theory without doing something else. And the diagnosis is going to be the following. After we've cured the illness, we figure out what's wrong with it. And what's wrong with it is that for every, when we do integral d a mu, there's a lot of copies. There's an infinite number of gauge copies. In the path integral. And normally, if you have an infinity, you just factor it out in front and you don't care. It's okay. But it doesn't seem to factor out. So you're basically just stuck with integrating over infinities in ways that are uncontrolled. And so basically, if you remove these gauge copies, you're going to get something that's better behaved. And in a sense, you know that from up here, if I just got rid of this term here, if I fix the gauge by setting d mu a mu equals to 0, I then have an easy way to invert that. So my sickness goes away if I fix the gauge. So one has the sense that you do the same thing here. For many years, people went along and just blindly fixed the gauge, and it turns out to be okay for QED, but not okay for Yang-Mills. So we'll do it right here. Okay, so that's what we're headed to. Okay, let's do the solution in a simplified example. Okay, so this is no longer field theory, but I do think it illustrates what we're doing. Let's imagine we have a two-dimensional integral of z is the integral dx dy e to the I s of x and y. Okay. But we're going to have a symmetry s of x and y is radially symmetric, just a function of the radius. Okay, so if we so in other words, phi doesn't appear. And we'd like to then factor out the symmetry direction from the important direction, which is the radial direction. Okay? Now, we of course can do it in this case, but there's going to be a fancy, let's do it in a fancy way. Which will work for gauge series. Actually, this is only half fancy. We get really fancy in just a second. I'm going to insert 1 is the integral d theta of delta of theta minus phi. Okay, so my variables here, I'm going to take x and y and change them into r and phi. So, okay, so for any phi that we're integrating over, I can do this. So I write z is the integral r dr d phi. I put in 1 is the integral d theta delta of theta minus phi e to the I s of r. Okay. Then I interchange the integration to integral d theta integral d2r delta of theta minus phi e to the I f, and let me call this w of theta. Okay, so this guy is constrained. So instead of for this, or z of theta, we're doing z's. So instead of doing the whole integral here, I'm just doing it along the radial direction, really. I've constrained it. But this is so that we now have integral d theta, z of theta, but that turns into just 2 pi z of theta because z of theta is independent of theta. Okay. So what we've done here, just it looks really overkill. I factored out that factor of 2 pi, and I've been constrained this integral to be along some subset. Okay, but this is, in a sense, what we want to do in the case of the gauge theory. We'd like to factor out all the gauge copies, all the gauge transformations, into some overall factor out in front, which will turn out to, of course, be infinity. And then just do the path integral over the constraint set that's constrained by some constraint. But to do that, you have to do this insertion of unity to do. Now, the following is more complicated, but closer to reality. For the gauge case. The trouble with the gauge case is that the symmetry direction is not a simple direction. It depends on every point in space-time, and you can do it differently in different points of space-time. So it's not a simple direction. So in this simple example here, instead of fixing the integration, the phi integration to phi is equal to theta, we're going to temporarily fix the integration to be some more complicated function, g of phi is equal to 0, or g of r is equal to 0. Sorry, it's a function of all the coordinates. G of r is equal to 0. Okay, so it's some path here. Now that works equally well. If you fix it at any given r, the angular integration is again a factor of 2 pi. But so we want to impose the constraint g of r equals to 0 instead of just the simple constraint. So now if we let r of theta equals r and phi plus theta. So in other words, where theta rotates this by a little bit, we have this identity, the equivalent identity is the integral d theta, which is what we want to do. G of r, and that's the one, g of r of theta so in other words, this will fix when theta is chosen properly, this near 0, this fixes that constraint. But the trouble here is that this is not a simple constraint. If I just did this, this is not one, because the integral d theta of this thing, which is a function of theta, doesn't give me one in general. What you have to do is you have to add in the Jacobian. It's dg d theta at g is equal to 0. Right? In other words, if I had done, or if I just did d theta delta of g of r of theta, that turns into 1 over absolute value d g d theta at g is equal to 0. Right? So in general, if I have a complicated constraint and I don't get one, I get the derivative. Yes?
Do you sum over all different points where it's 0?
At a given r, there's only one point. Okay, so we're assuming that there's just a single point at a given r. So this in general will be a function of the radius. Okay? Okay. So if I repeat the steps I did above there, then z is the integral d to r, the integral d theta, dg d theta, delta of g of r of theta, times e to the I s of r, becomes the integral d theta of z of theta again. But now, with z of theta is the integral d2r dg d theta delta g of r of theta e to the I s of r. Yeah, if you do it, thank you. Okay. So for this problem, this is extremely painful. But it does manage to factor out the symmetry direction, and it leaves behind a constrained integral. But the important point for this whole procedure is you can't just impose the constraint. So if you just naively went in and said, I'm going to fix the constraint on the path integral, that's not quite right. There's this factor here, which makes it a true equality. Okay. So I not only have to put in the constraint, I have to put in this Jacobian factor here. Okay. So this is we're now going to generalize to lots and lots of variables. The gauge theory version of this is we're going to have a lot of constraints. F, some function on a mu, we can set it equal to 0. So this will be the constraint that sits inside the delta function. But this is one at each point in space time. So basically you impose this point. It's a lot of constraints. It's not just one. Then in the identity that we want will follow from letting this thing have a gauge transformation. This is our symmetry direction. So a mu goes to a mu of theta, which is, for QED, it's a mu plus d mu theta. And if we want to factor out that gauge direction, we'll want the identity to be 1 is the integral d theta, so there's 1 at each point in space-time. This is going to be the Jacobian delta of A in general, times delta the function A of theta equaling 0, where delta of A is the Jacobian, is the determinant, the f d theta, evaluated as f equals 0 in principle. Okay, so when you have multiple variables here, this piece becomes the determinant of the transformation from theta to f. That's what this factor is here. And so there's our identity for gauge theories. This will be something, an example would be f of A is d mu A mu. Okay. So we impose that. I'll show you, we'll come back and actually maybe we'll even do it soon, calculating that determinant. Okay, so what I'd like to do now is to show you that it works, that this works in factoring the factors out the gauge transformations. Okay, so let's just do it. We have z, which is the integral dA, and for ease in writing, let's just keep the right here, either the I, integral d for x, the Lagrangian. It doesn't matter too much. We'll then write this, adding this identity, d theta, delta of A, delta of f of A. Okay, so f of A of theta. Okay, if I can show you if delta of A is independent of theta, okay, which I'll show you soon, then you can factor out which, remember, is the gauge transformations. And then when you do that, you've left behind the constraint, and so you've factored out all the gauge transformations, left behind only those A's that satisfy the constraint. Okay, so this then, you integral d theta of x is some number, it's infinite, but we don't care about it, and we have behind only the constrained A's. In the path integral. Okay, so then we end up with the final of J, which has this constraint f in it. It's some infinite number integral dA this Jacobian delta of f of A and e to the I integral d4x Lagrangian, and we can of course add in the J mu A mu piece, and then you can then do perturbation theory. You can then get an inverse. So if you chose f to be that gauge condition d mu a mu, then up here the d mu a mu piece disappears because it's always 0, and you can invert the simplified equations of motion. All right, I think the right thing to do is just let me do this last little piece of logic here to show you that this Jacobian is independent of the angle theta, or the gauge transformation theta. It's gauge invariant, and then we come back and make this concrete by doing real cases. Okay, right now it looks really formal because we've got all these formal determinants, but when we come back we can next time put in what this is in practice and write out QED and Yang-Mills theory. Okay, so here's the check that delta of A is gauge invariant. All right, so basically we're doing this integral d theta, path integral d theta, some delta of f of A of theta. That's delta minus 1 of A of theta, of A. Okay, that's our definition. What happened if we rotate this if I try rotating this? So delta minus 1, A of some theta 0. I'm going to take not A, but a gauge transformation of A. Okay, so A of theta 0 means I've made a gauge transformation on A by some function theta 0. So that then is equal to d theta delta of f of A theta 0. Okay, so I make a further gauge transformation theta on top of one that I already have. Okay, that's formally what that means. But then I let theta 0 be called theta prime. Since I'm doing the integral over all theta, that's the integral over all theta prime. And this formula then reduces to the integral d theta prime, delta of f of theta prime of, f of A of theta prime, which is just our original definition of delta minus 1 of A itself. Okay, so all this fancy stuff is basically just saying that this is gauge invariant, that if I made a gauge transformation on it to begin with, I'd get the same Jacobian. And the reason is just because we integrate over all possible gauge transformations. So if you started anywhere on that, you get the same answer. It's just like integrating over all space. If you shift things by an amount, you get the same answer. So since you're integrating over all possible gauge transformations, you can start at any given one and you get the same answer. And we'll see that. All right. So a lot of formalism today. We'll come back next time and make this more concrete by first doing QED and then doing Yang-Mills.